Welcome back, physics enthusiasts. I'm Swati, and in this video, we are going to do some derivations, important derivations on topic moving charge and magnetism. So, these are the 5 derivations which we are going to cover in this video. So, let's begin with that. Okay, so the first derivation is magnetic field due to long straight current carrying conductor. So we are calculating the magnetic field using Biot-Savart law. Magnetic field due to long straight current carrying conductor. So initially we are considering a finite one. Okay, so consider a long straight current carrying conductor of some length, and at a perpendicular distance from it, at a distance r, we have to calculate the magnetic field. Okay, now consider I current is flowing through it and a current element here of length dl, and joining these 2 points, and let's take it is making some small angle d phi here, and this complete angle is phi, and this angle here is theta as per the Biot-Savart's law. And from this point, this length is L. So consider a wire, consider a long straight wire, okay, carrying a current I, and the magnetic field at a point P, at distance r, perpendicular from the wire, can be calculated using Biot-Savart's law. It is just a language. You can manage it by yourself. Can be calculated by Biot-Savart's law. Okay. Now, as per the Biot-Savart law, according to Biot-Savart law, your magnetic field due to small element dl, of length dl, is basically equals to mu naught upon my 4 pi ideal sin theta by r square. So I dl sin theta, and that r square is basically this distance. Let's take this as x. Now, if this is r, this is l, so then this x is basically x square plus r square plus l square, Pythagoras, but I'm taking it in as a variable of x. Now, to calculate the total magnetic field, we have to integrate this term. To integrate this term, dl is a variable, okay, and we have to replace the sin theta also, and then x is also changing, because if the wire is this, then x, the value of x changes because l is changing. So we have to substitute all these things. So what we can do, we can substitute one by one. Okay, so first consider from here that this theta, this is 90 degree, okay, and this is 180 minus theta. So either you can do that, or you can simply write that 90 plus phi is equals to theta, exterior angle. So theta is equals to 90 plus phi as per figure, and then sin theta would become sin 90 plus phi, and 90 plus phi gives you cos phi. Okay, so you substitute the value here. Now we have to substitute this dl. So for dl, I'm using this L, R and phi. What I'm doing, I'm converting everything in terms of phi. R is constant here because the distance from the wire to the point is fixed. So I can use 10 phi for L by R. So second is 10 phi is equals to L by R. So your L is equals to R 10 phi. And we have to substitute for dl. So let differentiate it. Differentiate it. So you'll get dl. R is constant. Just differentiate 10 phi, which is x square phi, and d phi. Okay. And then for x, sorry, for x is hypotenuse. Again, R is a constant. So we can use cos phi. So third is cos phi, which is base upon hypotenuse. Base is R. This is the angle, and hypotenuse is x. So it's R by x. So simply your x will be R over cos phi, that is R sec phi. Now you can substitute the values here. This is x square in equation 1. Okay, so you can write substitute all the values in equation 1 and you get dB as mu naught over 4 pi I. dl can be written as R sec square phi d phi. R sec square phi d phi. Then what you have, sin theta can be written as cos phi. Then what you have, x square can be written as R square sec square phi. Okay, you can just cut the values and dB come out to be mu naught over 4 pi I cos phi d phi, and then you have R here. Now this I and R is also constant, so we can differentiate it, integrate it over the limits of phi. Okay, so integrate the term for the total magnetic field, due to wire under the limits. If I want to check the limits, then we have to put the limits of phi. So if this is my wire and this is the distance, let's say R point P. So let's join these endpoints because my phi will move from this point till this and also to the other end. Okay, so if this is a perpendicular wire, so you have to just raise the perpendicular wire to touch the one end and to touch the other, and that means I am basically raising this to this level and then to that level. So this is basically what, anti-clockwise. Yeah, so you can take in a other way around. You can bring this to the perpendicular line and you can take this to the perpendicular line. So the line joining the point where you have to calculate magnetic field to the endpoints of the wire, just start from there and bring it to the perpendicular line. That is a line which joins the point and the wire. So this is anti-clockwise, so take it as phi 2 positive, and this is clockwise, take it as negative minus phi 1. Okay, so under the limits minus phi 1 to phi 2. Okay, and kahan se hai, this should be clear to you. Okay, that is from the line to the perpendicular line always. So just integrate it, integrate dB, you will get B total, and that is equals to from minus phi 1 to phi 2, and you have to integrate mu naught I over 4 pi R, which is a constant. You can take the term out into cos phi d phi. So only you have to integrate cos phi d phi. So this becomes mu naught I over 4 pi integrate cos phi, you will get sin phi, and then you have to put the limits phi 1 to phi 2. So your magnetic field is equals to mu naught I over 4 pi r sin phi 2 minus sine minus phi 1. And you can take this minus sign out and it become positive. So B is mu naught I over 4 pi r sin phi 2 plus sin phi 1. Okay. Now, there are some cases here that is for infinite wire. If the wire gets infinite, then you don't have the endpoint. So the angle here becomes more parallel. That is, both phi 1 and phi 2 become 90 degree. And if they become 90 degree, then your B would become mu naught I over 4 pi r. Sin 90 plus sin 90 is 2. That is mu naught I over 2 pi r. Okay. If you check for semi-infinite, wire, and you have to calculate at its one end, that is, one is infinite, other is finite, and you have to calculate at one of its end, then your phi 2 will become 90 degree. This upper, it's parallel, you don't know where it ends, and the other, this becomes 0 degree. That is, phi 1 is 0 degree. So if you need to calculate B, then sin 90 is 1 and sin 0 is 0. So it's 1 plus 0 is 1. Then it becomes mu naught I by 4 pi r only. Mu naught I over 4 pi r. Okay. So this is for semi-infinite wire. Now if you want to calculate at perpendicular bisector, that means both the angles are equal. If this is the wire, which is a finite one, and you have to calculate somewhere in between, that means this angle and this angle is equal. Both have phi. Phi 1 is equals to phi 2 is equals to phi. And if this length is L, this is R, then this becomes L by 2. And this becomes R square plus L square by 4. Okay. So here the magnetic field becomes mu naught I by 4 pi r. And sin phi plus sin phi will gives you 2 sin phi. Sorry. You can cancel 2 and you can put the value of sin phi here, which is perpendicular upon my hypotenuse, that is L by 2 over under root of R square plus L square by 4. You can solve it a little more, which is mu naught I over 2 pi r L over under root of 4r square plus L square. 4 comes out of the square root. It becomes 2. This 2 and that will cancel each other. And this is the magnetic field. Okay. So these are some of its cases. And if you need to find the shape of the magnetic field lines. So if this is the current carrying conductor, then the magnetic field lines are concentric circles which are closer near the wire, and it gets far apart as we move away from the wire. Okay. And the direction you can calculate as per the right hand thumb rule, clockwise or anti-clockwise. So this is our first derivation. The second is magnetic field at the center of circular current loop. This is very easy. It's a very small one. So second is magnetic field at the center of circular current loop. Yeah. Circular current loop. Okay. So you have a circle carrying some current I in anti-clockwise direction and is a radius of r. So here you can consider a circular loop of radius capital R carrying a current I, carrying the current I moving in anti-clockwise direction. Okay, so again here consider a small element dl, consider a small element of length dl and magnetic field at a distance r can be calculated using Biot-Savart's law. So magnetic field due to this small element, at a distance capital R can be calculated using Biot-Savart law, which is dB is equals to mu naught upon में 4 pi I dl sin theta over capital R square. Now here theta is 90 degree. Always remember when you work in a circular path, then that theta is basically the angle between R and the current element. So this current element is always tangential, right? And if the current element is tangential to R, then theta would be 90 degree. You can say that IDL is tangential to R, is tangential to capital R for circular currents. Okay, so your dB will become mu naught upon में 4 pi IDL sin theta will become 1 over R square. Now here everything is constant. Mu naught I is constant, 4 pi R square is constant. So the integration is very easy. All we have to do is integrate dl. So the total magnetic field would be integrated dB. You will get total B, which is basically the integration of dl only. And if you want to integrate dl, then it is the circumference of the circular loop. Then your B would be mu naught I over 4 pi R square. Integrate of dl gives you 2 pi capital R. Simple circumference. And you can cut the values here. And the only thing is mu naught I over 2R. And if you need to find the direction, then if the current is moving in anti-clockwise, the magnetic field is upward. If it is like clockwise, it would be downward. So here the magnetic field is upward, or you can say vertically. Okay, so it's very simple. Now next is to determine the magnetic field on its axis, on the axial point of this circular loop. Okay, so the third equation is magnetic field on the axis of current carrying circular loop, on the axis of a circular current loop, on the axis of a circular current loop. Okay, so now you have this current loop and it is somehow placed in this xy plane. This is x, this is y. It has a radius of a and at a distance of r on z axis. You have to find the magnetic field. Okay, so what you can say that consider a current carrying, the current is flowing here like this, I have some problem in anti-clockwise and clockwise sense. So, anti-clockwise. Consider a current carrying circular coil of radius A placed in xy plane, placed in the xy plane में. Okay. Now the magnetic field at a distance r on z axis. This is not x, this is z axis. So to determine magnetic field at a distance r on its axis, we consider a small element of length dl. Okay. We consider a small element of length dl. Okay. So now consider here this small element dl and also here this small element dl. Now with dl, let's say the magnetic field is this, which is basically perpendicular to it. Okay. So, okay. So join this and you can join this, and the magnetic field due to this is basically perpendicular. So it is not vertically opposite. It is somehow goes perpendicular. Okay. dB and also perpendicular to this, which is dB. Now, if here the angles are phi, then as per the geometry, this angle would be phi. Okay, because this complete is 90, this 90 minus phi, and it gives you phi there. And similarly, the other phi is here, and if you resolve dB, then dB sine phi plus dB sine phi will come here, and dB cos phi, another dB cos phi will goes in a vertical sense. Okay, so the magnetic field due to small element has two components of field. First is along axis, z axis. So I'll take it as axis, which is 2 dB sine phi. Okay. And the other are verticals, which are same and they cancel each other, dB cos phi, dB cos phi. So dB, the vertical one, is 0 because it is dB cos phi minus dB cos phi, which is equals to 0. Okay. So from first, you can see that dB on the axis is equals to 2 dB sine phi. Now you have to put the values of everything, dB and sine phi. So as per Biot-Savart law, your dB is mu naught I IDL sine theta by 4 pi, and this is r square. Now here the r square is what? This is r, this is x. So this is your r square plus a square. Okay. That is r square plus a square raised to the power 2. Now again here theta is 90 degree. Why? Because you have taken the magnetic field to be perpendicular to this. Or you can say this length and DLA is tangential to each other, because this gives you this tangential. If this is my circular loop and this is the wire, so the theta will gives you 90 degree here, then dB would be mu naught I over 4 pi dl, and this is r square plus a square. Everything is constant, r constant, a constant, dl is a variable. And next substitution is sine phi. So sine phi can be calculated using this diagram. If this is phi, you can use perpendicular upon hypotenuse. Perpendicular is a, hypotenuse is this. So the sine phi would be a over under root of r square plus a square. So you can substitute both the values in equation 1 mein here. Okay. So substitute the values of dB and sine phi in equation 1, and you will get dB on axis is equals to 2 times of this mu naught I over 4 pi dl r square plus a square, and for sine phi is this. See here, the thing is, all you have to check which are constant, which are variables. Those which are variable you have to substitute it, which are and you have to bring everything into one variable so that you can integrate it. Now here you can see that everything comes in terms of, everything is constant except dl. So this is 2 mu naught ia, all are constants, over 4 pi and r square plus a square to the power 3 by 2. 1 plus half is 3 by 2 and dl. Okay. So integrate it. Integrate the equation, will get b along axis, and that is the integration of dB. Okay. So just integrate it over dl. So I can put everything out because everything is constant. And if you integrate dl, then you have to remember that you have already taken dl on both its end. Okay, so if you want to integrate it, you have to integrate on a semicircle, because this is due to both the dls you have taken on the circular ring and circular loop, and if you integrate again at whole, it would be 2 times. So just integrate it on semicircle. Either you take only dl and then integrate it over whole ring, or you take 2 dls and integrate over semicircle. Both gives you the same value, but you have to understand it, what you have taken and where you have to integrate. 3 by 2 and integration of dl will gives you as is 2 pi r, and here it's pi r and pi a because of semicircle. So pi and pi cancel each other. This 2 will give me, will also cancel each other. So it is mu naught I a square over 2 r square plus a square raised to the power 3 by 2, which is a formula of magnetic field on the axis of a current carrying circular loop. Okay, I hope this helps you. Fine. Now again, we have some cases here. The first one is at the center. Very easy. If you have to calculate magnetic field at center, then R is equals to 0. And if you take R to be 0, then B would be what? This 0, this A to the power A square to the power 3 by 2 gives you A cube. So it is mu naught I A square over 2A cube, and this cancel and comes out to the same value which we have derived earlier, like this also. The second is, let's take when R is equals to A. This is also very important. So here your B will become mu naught I A square over 2, and this is A square plus A square, that is 2A square to the power 3 by 2. Okay, and this is mu naught I a square over 2, and the 2 to the power 3 by 2 gives you 2 root 2, and a square to the power 3 by 2 gives you a cube. So this will cancel, and this comes out to be mu naught I over 4 root 2a. And if you have taken a very large distance, that r is very, very greater than a, very long distance, then your b would become mu naught I a square, and you have to neglect the value of a here. So it's simply 2r to the power 3. Okay, so you can ignore a, and this is what your magnetic field at a very large distance on the axis. Okay, so these are some of the very standard results of magnetic field on the axis of a circular loop, and they are important because they come directly in MCQs and everything. I've posted one video today on about MCQs on this moving charge, and you can see these all the formulas are of much use there. So you have to remember the end results and the derivation, because if there's a derivation, you can write it well, and if they ask in MCQs or in 2 marks questions, so you can directly use the formula there. Okay, so next derivation is to calculate the magnetic field inside a straight solenoid using Ampere's law, and then the force between two parallel current conductors. These two derivations is there. Okay. The fourth one is okay. So the next is magnetic field inside a long straight solenoid. Inside a long straight solenoid. Okay, so we are doing this using Ampere's rule. So consider this solenoid. Okay, and you know that inside the solenoid the magnetic field is uniform. A uniform magnetic field is there inside the solenoid, and it behaves also as a bar magnet, right? So now to calculate the value of this magnetic field, we are using Ampere's law. Okay, so to determine the value, to determine the magnetic field, to determine the magnetic field inside the solenoid, inside the solenoid, consider an Ampere's loop. Consider an Ampere loop of dimension L into B, of dimensions LB. Length L is length and B is its breadth. Okay, that means you have this solenoid. I'm just making a bigger one, and let's take this as my loop. Okay, let's see this, and take this as a loop. Okay, of length L and breadth B. Now the magnetic field is like this. Okay, so now here we have to take something like consider the current I is flowing in the solenoid. Consider the current I is flowing inside the solenoid, having n turns, n total turns. Okay, and small n be the number of turns per unit length. Number of turns per unit length. Okay. Now using Ampere's circuital rule, B dot dl is equals to mu naught I enclosed. Okay. So we are doing this for PQ, first for PQ, then QR, then RS, then SP. So for PQ, initially PQ, you can use B dot dl is equals to mu naught. And what would be the I enclosed? If for one wire, one loop, I current is flowing and total number of turns is N, then total I enclosed is N times of I enclosed. Okay. And if this is B and you have to integrate over dl, so the length of PQ is L only. So it's mu naught Ni, and this BL is equals to mu naught Ni, and then B would be mu naught N by Li, and N by L is what? Number of turns per unit length, which we have defined as small n. So mu naught small Ni. This is for PQ length. Now, if you go for QR, then it would be 0 because the length QR is perpendicular to magnetic field, and similarly with SP also it is of 90 degree. So if you consider B dot dl is equals to mu naught I enclosed for length QR, then this will become B dl cos 90 degree. Here it is 0 degree. So if I haven't mentioned, you can write as BDL cos 0 degree. Cos 0 is 1. So this gives you 0. So B for QR is simply 0. And similarly, if you move for R2S, here there is no current because it is outside the solenoid. So I enclose is 0 here. B DL cos 0 degree, but mu naught I enclosed is 0 here. No current. So here also the magnetic field is 0, and similarly if you are coming back to SP, it is again 0. For SP it is BDL cos 90 degree, which is 0, so there will be no contribution of magnetic field. So every length is giving 0 contribution except PQ. So B net would be only mu naught Ni. Okay, so inside the solenoid, the magnetic field is mu naught Ni, and at the edges it becomes half. Okay, mu naught Ni by 2, and as a very amazing graph which you should remember, the graph with distance and B, it is somehow like this. Okay, so this is a maximum value of mu naught Ni, and here it becomes half. Mu naught Ni by 2. Okay, so at the edges it becomes half. For CBSE, you don't have to remember that and how it's coming. Just remember that the graph is important. Okay. Now we have the last one, force between two current carrying parallel wires. Okay, force between two parallel current carrying wires. Force between two parallel current carrying wires. Actually, the numerical based on this topic is more important than the derivations. Remember that. Earlier, the derivation often come in CBSE, but nowadays, what I'm seeing is the numerical part from this topic is more there. So just, anyways, we'll do it's very simple. Okay. So here, consider two wires. Okay. Consider two wires first and second carrying current I1 and I2. Let this current I1 and this is carrying current I2 both in parallel direction. Okay. And they are separated by some distance A. And let's take the wire to be infinite for a while. But you will see the infinity won't change anything. Okay. So consider two um, parallel current carrying wires, two parallel wires carrying current I1 and I2, carrying current I1 and I2 separated by a distance A, separated by a distance A. Okay. Now we have to calculate the force between these two wires. So the force is ILB sine theta. So first we have to calculate the magnetic field. So magnetic field due to first wire on second would be, so we are calculating the magnetic field due to first wire, and if it is a infinite, so you can use the formula as mu naught I over 4 pi r, sorry 2 pi r, and r is a distance, so it's I1. Now if you want to check the direction, use the right hand thumb rule and it will go like downward cross. Okay, so now you have the magnetic field, and for the force, now the force on wire second due to first, because you have calculate the magnetic field on second wire due to first, so that field will apply force on second wire, that is force on second wire due to first would be ILB sine theta. I would be second, B due to first, take length L. Okay, on length L we have taken some length L here, and sine theta. Now theta is the angle between L and B. L is like this and B is vertically downward, so theta definitely goes to 90 degree here. So F21 is basically equals to I2 B1 L, and you can put the value of B1 here, which is mu naught I1 2 pi A, mu naught I1 over 2 pi A into L. And if you want to check the direction, you can use Fleming rule, and this is the magnetic field which is downward, and this is the current which is going upward. The thumb is pointing towards the first wire. This is the force on 2 due to first. So you can define as force per unit length. Now the length doesn't matter because we have actually taken at per unit length. So if it is infinite, you can take any portion of length per unit length, and that comes out to be mu naught. Just remember this formula, it's important. You can find, I think, some numerical of this formula, and the direction would be towards first wire. Similarly, you can calculate the force on first wire due to second. Similarly, first you have to calculate magnetic field B2, that is the magnetic field due to second wire, and it is mu naught I2 over 2 pi A, and if you want to check the direction, it is upward. Here it is upward, and the force per unit length, okay, on wire first due to second is basically F12, which comes out to be ILB, that is I1 L and B2 sine theta, and theta is 90 degree here. So this is I1 L, and that B2 is basically mu naught I2 upon में 2 pi A. So force per unit length would be mu naught I1 I2 over 2 pi A. And if you want to check direction, again Fleming left hand rule, magnetic field is upward, current is like this, then the thumb will gives you this direction. That is, both the forces are this towards each other. That means they are attracting in nature towards wire 2, towards second wire. That means the parallel current, the wires having parallel current attract each other. Parallel current carrying wire attract each other. Okay, with equal force, and that is F12 is equals to F21, and that is equals to mu naught I1 I2 by 2 pi A. Mu naught I1 I2 over 2 pi A. Okay, so if the currents are anti-parallel, then they will repel each other. So you have to remember this. Anti-parallel current carrying wires repel each other. Repel each other. Just remember this. Okay, but this particular thing is more important for numerical and concept based, but it's very easy. The derivation is very easy. You can remember that. All you have to do is to find the magnetic field, because the first wire will put the magnetic field on another. That magnetic field put force on this wire. Okay, so these are some of the important derivation from chapter Moving Charge and Magnetism. And next we will do on magnetism plus electromagnetic induction, and then AC and electromagnetic waves. So thank you for watching this video, and do like, subscribe and share and comment below. And we'll meet you in the next video.